Start recording. All right. So this may seem familiar if you were in my class last year, because this is like the same first few slides here. We got a car that's traveling at a variable rate from t equals 0 to t equals 2 hours, and we want to know how far the car traveled during those 2 hours. How do we figure that out? What is the total distance that the car went? I don't need a numeric answer right now, just how would I figure out what it is? Right, should just be on an area underneath this curve, right? Should just be whatever this area is. And obviously we know that the area underneath the curve can be found using an integral, but we're going to quickly go through the different ways to approximate an integral when we're just given a graph or given a chart, and how we can use those area approximations from underneath the curve to develop the idea for an integral. So first method of approximation is the left rectangular method. Left rectangular method means start at the left endpoint, which in this case is 0, go to the point at 0 and make a rectangle. Then go to the left endpoint of the next subinterval, make a rectangle. The left endpoint, that was not in the right spot. The left endpoint of the next subinterval and make a rectangle. And the next one, 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 and the next one. Oh, I think I put one too many in there, didn't I? Good enough. That last one looks horrible. Pretend those are all really nice rectangles. Right? We find the area of each of the rectangles, we sum together those areas. That gives us a decent approximation for the area underneath the curve. Is it perfect? No. But is it good enough? Sometimes. What do we remember about left rectangular approximations? First off, when our function is increasing, then what does our left approximation do? Yeah, if our function is increasing, it should be an underestimate. And if our function is decreasing, it should be what? It should be an overestimate. Yeah, and you should be able to see that from the graph. Whenever my function is increasing, I'm underestimating it. And whenever my function is decreasing, it's an overestimate. Everybody good with that? All right, what about the right rectangular approximation? Same thing, right? Except that we start on the right endpoint and make our rectangles. Pretend that my rectangles actually look like rectangles. It's hard to draw on the laptop screen, right? A right rectangular approximation method. This is the one that we normally use to develop the actual integrals. And what happens when f is increasing? Our right rectangular approximation is a overestimate, and our right rectangular approximation is an underestimate when our function is decreasing. Good? Any issues with that? All right. And then we have the midpoint rectangular approximation method. So find the midpoint of each subinterval and draw a rectangle through that point. And this one is a better approximation than both the left and the right rectangular approximations, but it's still not perfect, right? And we'll note that this one, we get some pieces that are outside of it and some pieces that were, some pieces that are extra and some pieces that we're leaving off. And so whether the function is increasing or decreasing, it doesn't actually tell us whether it's an under or an overestimate. Everybody good with that? All right, so we're going to take x squared, simple function, f of x equals x squared from 0 to 3. Using 3 subintervals, we're going to approximate using a left, a right, and a midpoint rectangular approximation. So you guys are going to do this, then we're going to check and make sure you got the right values and make sure you put the right stuff in. So take 2 to 3 minutes and do each one of those 0 to 3, 3 subintervals, a left, a right, and a midpoint rectangular approximation, just so I know that you can do them. Ready to go. So for our left rectangular approximation, our first left endpoint is 0. So 0 squared, right? That's the height at 0. And then the length of the subinterval is just 1 unit, so 0 squared times 1. The next one is 1 squared. 1 squared right here. Here's our first one. Second one is 1 squared, so 1 squared times the length of the subinterval, which is 1. And the last one is 2 squared. 4 times 1 gives us 5 overall. Everybody good with that? The right approximation gives us 9, 4, and a 1. Three squared times 1, height times length of subinterval, height times length of subinterval, height times length of subinterval. And what does that come out to be? 14. And with the midpoint, the midpoint of 0 and 1.5, 1/2 squared is 1/4 times the 1. Midpoint of 1 and 2 is 3/2, squared is 9/4 times 1. And the midpoint of 2 and 3 is 5/2, which squared is 25/4 times 1. And what does that come out to be? 35/4. A little bit less than 9. And I think we should know that what the actual value of this should be. What should the actual value be? 6, Adrian? No. Yeah, don't take a derivative. This is the other direction now, right? X squared becomes 1/3 x cubed, right? So the actual value should be 9, right? Yes, it should be. All right. The other method that we use for approximating these integrals is the trapezoidal rule, right? Everybody remember the trapezoidal rule, hopefully. You just take the endpoints and you make a trapezoid. So the endpoints of the interval, connect them with a line, and make a trapezoid. So 2 different ways to do it. One is if you have unequal subintervals, just find the area of each trapezoid and sum them together. The other option is if you have equal subintervals, you can go through and you can do the common height, h times y naught plus y1 over 2, and h times y1 plus y2 over 2, and so on. Or if we factor out the h, that becomes h over 2 times y naught plus 2y1 plus 2y2, all the way down to 2y sub n minus 1 plus 2y sub n. Everybody good with that? Remember that rule? If it crosses the x-axis partway through the subinterval, that's fine. Depends on if we're talking about approximating the area or approximating the integral. So we'll talk later today about that a little bit, but remember that when you're talking about, the last one does not have a 2. Did I say? Yeah, it's not supposed to have a 2. Thank you. I don't know. I didn't say a 2, did I? I think I just wrote the 2. I don't know if I said the 2 also. That was stupid of me. I don't know why I put a 2 there. Anyway, Molly, to answer your question, it doesn't really matter if it crosses. You still use those points. If we're talking about the area underneath the curve, then remember that we're talking area, then this stuff, we just count this as all positive. But if we're talking about the actual value of the integral, then everything that's below, we talk about it as negative. And how do we find the h value? H is equal to b minus a, right? Endpoint minus starting point divided by n, where n is what? N is the number of subintervals. And so anytime we're talking about h, the length of a subinterval, it's always going to be b minus a over n whenever we're doing these Riemann sums. Everybody good? What if we went back here and tried to use the trapezoidal rule? Using the trapezoidal rule, what should we have? We should have the height, the length of each subinterval, which is what? B minus a, 3 minus 0, over n, number of subintervals, divided by 2 times what? The first y value, which is 0, plus 2 times the second y value, which is 1, plus 2 times the next y value, which is 4, plus the last y value, which is 9. And what does that come out to be? It comes out to be half of whatever this all is. Comes out to be 19 over 2. And we'll note that the trapezoidal approximation is always an average of the left and the right hand rectangular approximations. Good or no? Yeah, the trapezoidal approximation is always the average of the left and the right rectangular approximations. And how can we tell if a trapezoidal approximation is an under or an overestimate? Here's our function, right? We'll do something like that. There's our function, right? If we're doing a trapezoidal approximation, there's some intervals there, right? If the function is concave down, what do we have? We have an underestimate. But if the function is concave up, we're going to have an overestimate. Everybody good with that? So things to remember, right? Any issues there? All right, use the trapezoidal rule on this. Ready, go. So we've got b minus a, 2 minus 1 over n, 4 subintervals divided by 2. First y value will be 1 squared. All right, our subintervals are 1 to 5/4 to 3/2 to 7/4 to 2, right? So 1 squared plus 5/4 squared times 2, and then 2 times 3/2 squared, and 2 times 7/4 squared, and 2 squared. Everybody good there? Should give us 1/8 of what? 1 plus 25/8 plus, what's that one? 9/2 plus 49/8 plus 4. And what does that come out to be? Uh, 150 over 64. Is that right? Did I do that right? $75, 30 seconds. Everyone good? We all remember how to do this, I hope. Okay, so then the question is, how do we turn these Riemann sums into actual integrals? So what we do is we take a partition of a function from a to b, divide it into our n subintervals and label them out x sub 1 to x sub n. Pick some arbitrary subinterval, we call it the kth subinterval. And we draw our rectangles in there, and I'm going to draw the right rectangle. It's not that it really matters, but and so on. So this one looks a little weird. We'll just draw our little trapezoid thing inside of there, and then what we want to do is we want to find a way to get an infinite number of these little rectangles inside of here, right? And so we call all these little sums that we've been doing, these approximations, we call these Riemann sums, and all of them just come from taking the delta x value and multiplying it by the height of the function, right, when we're doing the rectangular ones. So if we take the kth subinterval, and we call that one the largest subinterval, and we shrink all of them down so that the subinterval becomes very, very close to 0, and then we evaluate the limit as the largest subinterval approaches 0, then that should tell us that all of the other subintervals are also approaching a length of 0. And if we evaluate that limit, it should give us an exact area underneath the curve. So what we're doing is we're taking each subinterval. In fact, we're taking the biggest subinterval, shrinking it down so that it becomes 0. And if we're shrinking all the other ones down at the same rate so that we're getting more and more subintervals, then they're all getting to be infinitesimally small. And you add together all those infinitesimally small areas to get the exact area underneath the curve, right? And effectively what we're doing is we're taking the limit as what we call the norm of the partition. So that's the largest subinterval. We call that one the norm of the partition. Taking the limit of that as it approaches 0 of the sum from the first subinterval to the nth subinterval of the areas of each of the subintervals, and that's our integral. If we were to make all of the subintervals the same length, then rather than having like 18 different variables in here and having to deal with a largest subinterval, if we made them all the same length, then instead of making the biggest one approach 0, we would just make the number of subintervals n approach infinity. And so we'd have the limit as n approaches infinity of the sum from k equals 1 to n of the height times the length of the subinterval. And this is normally what we consider Newton's notation for an integral, right? This is the notation he actually used. He didn't write out with the little squiggly bar that we get used to. That was Leibniz's notation. He just used limits to evaluate them. So everybody good and sort of remember where these come from by taking this limit as the number of subintervals approaches infinity of the area of each of the subintervals, or little rectangles in the subintervals. Everybody good there? Or questions there? Okay, so we know our integral sign, we got our lower limit, our upper limit. We call this the integrand inside of there. So our limit as n approaches infinity of the sum from k equals 1 to n of the area of each of the subintervals just becomes this integral notation. I think you should all be good with that. I hope. If I told you that we were taking an interval from -1 to 3, k equals 1 because it's the, we're labeling that out as like the kth subintervals, and k equals 1 means from the first subinterval. So we're starting at the first one and going to the nth one, the one at the end of our interval. Good, Nick, or no? Okay. All right, so if we have a limit as n approaches infinity of a sum from k equals 1 to n of 3 times m sub k squared minus 2 times m sub k plus 5 times delta x, and our interval is from -1 to 3, and these m sub k's are the midpoint of the kth subinterval, how could we rewrite this as an integral? We just say it's an integral from -1 to 3. Well, these m sub k's can just be converted into x's to become our function, 3x squared minus 2x plus 5. And our delta x just becomes a dx. It's the small change in x for each subinterval, right? The width of each subinterval. So this is the height of each subinterval. This is the width of each subinterval. We're multiplying them together. The summation tells us that we're summing together all of those little tiny areas from -1 all the way to 3. Good or no? Easy enough. All right, so I'd like us to take this integral here and convert it into Newton's notation. So how are we going to be going about doing that? Well, it's going to be a limit. It's going to be a limit as n approaches infinity of a sum from k equals 1 to n of the height of each subinterval, or the height of our function, times the length of each subinterval. So what's the height of each subinterval? It's just our function, right? At whatever k value we're at, 3x sub k. And what is the length of each subinterval? Well, it's just our delta x value. It does not look like a delta. It's just our delta x value. And so how do we find delta x? It's always equal to what? The length of the subinterval is always equal to b minus a over n. Exactly. So delta x is b minus a over n, which in this case is 2 minus 0 over n, or 2 over n. And how do we find the x sub k value? Well, what's the height of the first one? If we go over 2 over n, and then go up our function value. It should be 3 times 2 over n as our height. So our x sub 1 is just 2 over n. That's how far we went over. And then if we go over to the next rectangle, we've gone 2 over n for the first one, right, the length of one subinterval. And then we've gone over another 2 over n. So that'd be 2 over n times 2. And if we go to the next one, x sub 3, it should be 2 over n times 3. So if I go to the kth subinterval, it should be 2 over n times k, or 2k over n. Everybody good with that being x sub k? Any issues with that? Everybody good or no? All right, so here we've got 12k over n squared. The 12 is just a constant. Oops, I forgot my summation. The 12 is just a constant, and the n squared within this summation, n is just a constant. It's just the number of subintervals. So we can rewrite this as a limit as n approaches infinity of 12 over n squared times the sum from k equals 1 to n of k. And you should know what the sum from k equals 1 to n of k is, because you learned it sometime, somewhere. At least you did last year. If you were in my class, you should have learned it before then. What's the sum from k equals 1 to n of k? N times n plus 1 over 2, exactly. And so now this just becomes a rational function, right? 12 times n plus 1 is 12n squared plus 12n over 2n squared. It's just a rational function where the degrees of the numerator and the denominator are the same. So divide the leading coefficients, and you end up with 6. If you're not sure about where the sum from k equals 1 to n of k being n times n plus 1 over 2 came from, we can show you real quick. If I want to sum together all the numbers from 1 to n, right, that's what the sum from k equals 1 to n of k is. It's just summing together all the numbers from 1 to n. You can do it this way. Just write them out backwards. Sum them together. These terms become n plus 1. These terms become n plus 1. These terms become n plus 1. Every set of 2 terms becomes n plus 1. And since there were n integers here, and I've summed them with n integers here, well, these are also n of these n plus 1s. And my n plus 1s is double what I actually wanted, so we divide it by 2. We did that last year, but hopefully you've all seen that before, yeah? Everybody good or no? Anybody have any issue? Good, you think. All right. So let's do one more of these before we call it quits for the day. The integral from 1 to 4 of 4x. So what should that become? It should become a limit as n approaches infinity of the sum from k equals 1 to n of 4 x sub k times delta x. And what's delta x going to be? Should be b minus a over n, or 3 over n. And what is our x sub k value going to be? It ought to be 1 plus 3k over n. So we got to be careful. In the last one, we were starting at 0. So if I was starting at 0, right, for the first rectangle, I go over just from 0 to the end of that first subinterval, which in this case would be 3 over n. But that's not what I've got going on here. I'm starting at 1. So my first rectangle actually comes from 1 plus 3 over n. So our next one ought to be 1 plus 3 over n plus another 3 over n. Or our kth one ought to be 1 plus 3k over n. And so hopefully you remember from last year that the delta x value is always b minus a over n, and that the x sub k value is always a plus k times delta x. Everybody good? Good or not good? Okay. All right, so then when we plug it all in, four times our x sub k value, which was 1 plus 3k over n, and then times our delta x value, which was 3 over n. And I won't have you guys evaluate this one out. We could if we wanted to, but generally they only make you go this far on the AP test. So, any questions or issues with that?